Welcome everybody. In this video we're going to extend what we did in the previous video and apply it to section 12.3 of the Biophysics and Physiological Modeling book. And what we're going to talk about is probably the most famous model in epidemiology, the SIR model. And the thing about this model is it's kind of the origin of some concepts that you may have heard about online or in the news. And so the first thing is R naught, which is the basic reproduction number. And the other concept is herd immunity, which has had quite a lot of press in the last month or so. Alright, so let's start with the finite difference diagram of this SIR model, and as you can see it's named after the three boxes. Alright, so the three boxes are susceptible, so this is the same as what we've been talking about before. The rate at which you go from being susceptible to being infectious is the same as what we talked about in the previous video for the finite population model. And the new thing here is this rate constant and this box, which is for recovered folks. So the thing that we're adding to what we did previously is the idea that people who are infectious eventually will recover. And that happens with a rate constant, Kr, which is the recovery rate constant. And to get the rate, that's multiplied by the number of folks, Ni is the number who are in box I. Alright. Oh, and like I said, the main assumption is infected people can recover. Alright, so just to remind you, Ki is the infection rate constant, here it is, and it has units of per day. The next thing after that is the number infectious, which is the number in this box. Remember, to go from susceptible to infectious, you have to bump into somebody who's infectious. So that Ni has units of just a number. The next concept, which we talked about before, is lowercase s, is the susceptible fraction of the model population. It tells us the fraction of the population who are still susceptible to the disease. The last thing, and this is really the only new concept in the variables that we have, is Kr, which is the recovery rate constant, and it has units of per day, right? So it has the same units as Ki, and it tells you the rate at which a person who's infectious will recover. Okay, so now let's go to the chapter, and the place that we want to go to is on page 18. Here it is. So this is the diagram that we were just talking about. And the first question that we've got to talk about, let me just talk about this. This is just a bookkeeping equation. It says that the total number in the population is the number susceptible plus the number infected plus the number recovered. The arrow that goes from infectious to recovered has this rate, and that rate we're going to call Ri. And so that's what this equation 1216 is about. It's just reminding us the equation that we've already talked about. The next thing I want to talk about is actually called the mean infectious time. And what it is how long somebody stays in this box I, right? So how long on average does somebody stay infectious until they transition over to being recovered? And from chapter 2, we know that if you have just one arrow leaving, there's a concept called the mean residence time in a box, and it turns out that's exactly the same idea for the infectious box, and we'll call that the mean infectious time. And the way you calculate it, it's this Greek letter tau, and I have a video here, the Greek letters go green, that talks about how Greek letters are pronounced and written. Anyway, so here it is. Tau I is just the mean amount of time that somebody's infectious. Another way of thinking about that is how long after they become infectious does it take for them to recover? And it turns out that because of the way the math works, it's really quite simple. It's just the inverse of the reaction rate constant Kr. Alright, so question 18 says, using figure 1211, show that, right, so this is an algebra question, and what it's asking you to do is calculate the change in the number who are infectious during a short amount of time, delta t. Alright, if we go to my drawing program, I'm going to do this out by hand the way that I think makes sense. So this is the way I'd normally explain it to my students. So here we have a box, this is box S, and we have another box, and that one's red for the infectious folks, and then we have another box, green, for recovered. So we've got our three boxes that go with the SIR model, and we have rates that connect the boxes. So going from S to I occurs at rate Ki times Ni times the fraction S of the population that's susceptible, and then going from the middle box to the recovered box happens at rate Kr, which is, it's not rate Kr, it's Kr times Ni, that's the rate. Okay, so that's the diagram that we're going to use to derive the equation. The equation that we're trying to do is going to be delta Ni, because we're interested in this box, right? So I'm going to do that. And we have this arrow, and what it does is it makes the number infectious bigger, right? Because the arrow is going in, so it makes it bigger. So it's Ki Ni times S, which is the rate. If we multiply that by the amount of time we're thinking of, you get a number. So this is the number that the number infectious gets bigger by during the amount of time we're thinking of, delta t. We also have an arrow going that way, which decreases the number of infectious, and so that's a minus, right? Because the folks in this box are leaving and going that way, right? You can think about cars leaving a parking structure and going. When they leave, they decrease the number of cars in the building. So we have minus Ki times R times Ni, that's this rate that we're talking about, and then we need to multiply by the amount of time we're thinking about, and you get that. So that's the rate that you get just by inspecting this diagram. We can then rewrite that as delta Ni equals, and this thing we're going to call Ri, the rate of infection, times delta t, and this thing is the rate of recovery, which we're going to call capital R, lowercase r, subscript. And both of those are multiplied by delta t, and because we've got a delta t in both of these, we can factor that out and get that delta Ni equals Ri minus Rr multiplied by delta t. And so that is what we were trying to show, I think. Let's go back and have a look. It's always good to go back and check. And yep, here it is. So we've got, that's the equation we were trying to get. And then it says also show that this is true. So this is the way you do a show that problem, is you don't try to get the answer. What you try to do is understand what it's asking you to find. So the thing we're trying to find is this. It's the change in the number in the recovered box. And so let's go back to here. We'll look up at our diagram. It says, how does this box change with time? Well, we only have one arrow going into it, and that arrow is going in. So if it was cars entering a parking structure, it makes the number inside bigger. So we can go delta NR equals plus, and then we have to look at the rate, and it was Kr times Ni times delta t. And this thing, remember, we had a name for that. It was capital RR, so we can write delta NR equals R delta t. So the two equations that we just showed, that was the one we did before, and this is the one we just did now, and that's the answer to, let's have a look back here. Yes, here we go. So that was the answer to this question and the second part of the question. And then we have, oh right, so we're going to talk about algorithm instructions. So how do you do this? Well, this guy is just the equation that we talked about last time for the finite population model. This is the new one, and if you look at it, it has the same form as the equation that we were just talking about, this guy. Right, so I think that's fairly straightforward. And then the next equation, this one is just our update equation, so let's just talk about it. The new number infected is the old number infected, plus the change, which is the thing that we calculated up here, right? This was the change in the number infected. So this here is actually the same thing as that. Alright, so that's that one, and then the new number recovered is the old number recovered plus the rate that you make new recovered people, that people recover, times delta t. And then the last equation here, let's just quickly talk about that because I think it's useful. We have an equation which, again, I think I already mentioned it, is the bookkeeping equation. It just says that the total number is the number in the S plus the number in I plus the number in R. And so if you're interested in, which one were we interested in? We were interested in NS. So the idea is that if we try to find NS is just equal to N, right? Move these guys over by subtracting them. We get NN minus NI minus NR. Alright, so that is this equation. So now we've actually derived all of those. And part C says write out a complete FD diagram, a complete FD algorithm. And I happen to have done that before, so let me show you what I prepared. But you should actually try to write this out, right? Go through chapters 2 and 3 about writing algorithms and FD algorithms, and make sure you actually know how to do this. I'm showing it to you now because for this to make sense, you really need to have the algorithm right. So what I'm going to do is show you my answer. Where is it? There it is. Let's see. There it goes. Okay, so this is the algorithm. Let's just go through it again, and I'll make my dumb joke about param $sign not really wanting to be a wrapper, but the $sign there is to remind you that anything in this parameter column needs to have a $, something when you put it into Excel. The things that we have, N equals 1,000, that's our population, 1,000 people. Delta t, the time step, has units of days. The infection rate constant has units of per day, and its value is 0.36, just the same as before. Oh, not the same as before, we actually added a bit to it to kind of account for this. We'll talk more about that later. N naught is the number infectious on day 1, or day 0 actually, that's what the naught's for. Tau I is the infectious, the mean infectious time. So this is the amount of time that a person who gets infected is infectious and can infect other people. And then Kr is the recovery rate, and it's just 1 over tau I. Right? So we're only really counting people in box I while they're infectious. It doesn't count from when they first got infected. It starts, right, their time in box I only starts when they're infectious. All right, so we have the variables, and it's time in days, the infection rate in per day, the recovery rate in per day, and the numbers in the 3 boxes. Infectious, number in recovered, number in susceptible. In step 0, when we're setting up, right, we got these instructions. Set the time in step 0. New, remember, means the current step. is 0. We don't need rates because we're not doing anything in the first step. We do need to set up the number of that are infectious, and we're making that equal to n0, which we have over here as a parameter. The idea here is if you change the number in the parameters column, it gets transferred by the spreadsheet into step 0 automatically. Alright, and then the number recovered, we're assuming that nobody's been infected apart from this one, however many there are, n0. So that's 0. And then this is our bookkeeping equation that says, well, if we have a total population of 1,000, right, here's the 1,000, then you just subtract the number who are infectious, which in this case is going to be 1, and you subtract that. So this equation is kind of an important bookkeeping equation, and just to skip ahead, it's the same equation that we'll use in step 1. Alright, so in step 1, we increment time, so the new time is the old time plus the time step. The new rate of infection is Ki times the number infected in the previous step times the number susceptible divided by the total number. The rate of recovery is just the recovery rate constant times the number infectious. And then the new I is the old I plus the rate at which they increase, which is this expression, right? So it's using the new infection rate and the new recovery rate, and they're subtracted, right? Because this makes it bigger and that one makes it smaller, times the time step. The new number recovered is this, and it's equal to the old number plus the recovery rate, the new recovery rate, that one which we just calculated, times the time step, and then the bookkeeping equation which we already talked about. You're expected to do unit checks. In this case they're fairly straightforward. So the recovery rate constant is 1 over the mean infectious time, and this thing has units of days, and so it's 1 over days. Again, this is the same unit check we had before. This guy, the unit check is fairly straightforward. This one has units of per day. This guy has units of just 1. When you multiply them, you get per day, which is what you expect for a recovery rate. So that's good. Alright. Same thing here. We have the new number infected is the old number. So both of those are just numbers. This thing has units of per day, right, the thing in the parentheses, and it's multiplied by days, so that's this and that. So these things, when you multiply them, cancel, and you get just a number, and that's good. And then the new number recovered is the old number recovered plus the rate times the amount of time, and again we've got per day times days, and so the units come out good. And doing unit checks, particularly in biophysics, things can get kind of tricky because physiological folks use all kinds of interesting units that you probably don't come across anywhere else. Alright, anyway, enough of that. What are we going to do next? What we need to do next is just quickly talk about the output table. Now normally when I'm doing this with students, we talk about the output table, and the idea, and this is one of the things that's mentioned in the chapter and goes all the way back to chapter 2, is that while you're doing this, you should double check that this instruction actually does the correct thing to make the time, here we are, go from 0 to 1, right? It says add the time step. Well, the time step is 1. We started with 0, so it says take 0, which is this guy, add 1 to it, and when you add 1 to 0, you get 1, and so you only write the 1 after you've followed the instruction. And the idea is that you're testing the algorithm by doing it, just like, you know, testing the recipe for an omelette by making one using the instructions. Alright, so the same thing happens here with the rate. You go through and you just see check whether you've actually got all the stuff you need for this, and then fill in this number here when you get to it. And you have to go through each one of these numbers in turn, and actually the way you do it is you go through, do this instruction, and then transfer the number to the algorithm. So that's what that's about. So now what I want to do is get back to the chapter, and alright, so we're after you've done that, right, this is our thing that we were just talking about. We need to download the spreadsheet, and let's see, it should be in there. There we go. Click OK to download the spreadsheet. Hopefully it won't take too long. Alright, so now we've got the spreadsheet, and the first thing we need to do is enable editing so we can edit it. And then the next thing we need to do is we need to go through our algorithm. And what we need to do, I just need to find my algorithm because I need to read it too. The purpose of the algorithm is to make inputting stuff into the spreadsheet really easily. So you should have, at this point, a handwritten algorithm that you can use to enter the spreadsheet. So what I'm doing is going back to my model answer because I need it to figure out what to type in. Alright, so what we've got is we've got RI. Oh, we should go through and check all the things. So first thing, we've got our param $sign column, right? Not really a wannabe wrapper. Remember the $sign says whenever you talk about anything in this column, it should have $A because it's in column A, and then $3 if we're talking about N, and $A, $5 for this guy. Anyway, so N, capital N. Remember, in these materials, whenever there's a letter that stands for a number, you need to know what it is, right? So capital N is the population total, right? How big the population is. So 1,000 people. Delta T in days is 1 day. Ki is the infection rate in per days, and it's 0.36. N naught is 1, so that's the number that we're going to start the simulation. No, it's not a simulation, it's a model. Yeah, shame on me. You have to read chapter 3 to know why I'm kind of beating up on myself about that, because we're trying to use the word model for numerical models like this, and simulation for things that are like the marble game simulation that I showed you last time. Anyway, tau I is in days. It's the mean time infectious, so it tells you how long somebody's infectious before they recover. And then the recovery rate constant, which has a formula, right, and it's 1 over the mean infectious time. Alright, then initial time, so step 0, so we're going through that. Oh, so the variables are all listed up here in the columns, right? So time has a column, the infection rate has a column, the recovery rate, the number infectious, the number recovered, the number susceptible. They all have their own columns. That's what the variables are. And then in step 0 we have time. Time new is 0. We didn't bother with the 2 rates because nothing happens in step 1. Then we have the new number, so let's click in there and see what it is. So it's equal to $A. You can see this is blue and that's blue, so they match. And then have to escape, then click that guy, it's just 0. And then this guy, there's a formula for it, and the formula was that bookkeeping one that we were talking about. So it's $A, $3 is N, and F3, I clicked on it to get that. We'll talk about how to do that next. So that's what's already in the pre-formatted spreadsheet. Then what you're expected to do is fill in the blanks, right? So here's the first blank, and it's for the infection rate, and the formula for that is equals the infection rate constant, which is here in the parameters column. So we have to hit F4 on a PC, and if you're on a Mac you have to type in the $signs by hand, times NI, which NI old, which is that guy, times NI NS old, which is that guy, divided by N, which is a parameter, so we need to do F4, hit enter. And then RI, which is the recovery rate, which is equal to the recovery rate constant, and we have to hit F4 times NI old, which is that guy, hit enter. And then the new NI, this is our update equation, the new NI is the old NI plus the change, which is open paren the infection rate minus the recovery rate, close paren, times delta t, which is a parameter, so we have to hit F4. Hit enter, and then the new recovered equals the old recovered plus the new recovery rate, which is that guy, times delta t, which is a parameter, so hit F4 to get the dollars. Hit enter, and then the formula up here is going to be the same. So I have the open cross, I'll make it go to a closed cross, and then I can left click drag down, and that should work. Now, if all has gone well, I should be able to click in the middle of this guy and left click drag across to select it, and then I can go from my open cross to a closed cross, and then left double click and fill in the table. Yay! And it worked. Okay, it doesn't always work. So if it doesn't look the way you expect, then you have to go back and just double check that you inputted everything correctly. Alright, so this is our model, and let's go back to the question because it's been a while. So we've got the question, and it says open the pre-formatted spreadsheet, fill in the blank cells, should automatically plot. That's what we just did. And then it says, as always, you need to reduce the time step to be small enough and add steps so that the curves visually reach steady state at the end of the model. So this thing about reach steady state, where is it? Reach steady state at the end of the model means, let's have a look at the graph. It means that what we want it to do is down here at the end, we want the blue curve to get down to a flat line, and we want the gray curve to go up to a flat line. So these guys almost are making it, but we only have, just scroll down, takes a while, we only have 95 steps. So what we probably want to do is increase this, and I think what I want to do is make this, I think last time we did 5003, so let's try that and see how it works. So I'm scrolling down, 3000, I always go too far, 4000, oh, way too far, 5003, let's see if that works. Alright, oh, 5003. Why 5003? Can you see it? It's actually 5000 steps. So that would be 5000 days, which is like way long. Oh, see, and it auto-scaled, and it's like everything happens in the first little while. But we want to decrease this time step, and we had a time scale for this, and I'm going to cheat and just check to see what it was. Yeah, the one that I have in my answer, I went out to 160 days. Now, this is something where, in reality, what you want to do is do this by trial and error. So I'm going to change this to 160 days, and I'm going to do the same thing here. Now, part of the reason for picking that, you can actually see it. Let me just do this, and then I'll show you both of the graphs, and you'll kind of see why. So I picked them so that it stayed, you know, you can see down here it's actually fairly flat for enough time that we're confident that it's flat. Right here we just have a little jag up just there. So this last, you know, what is that, 30 days, it's staying really pretty flat. Alright, so now what we want to do is we want to adjust the number of the size of this time step to see how it goes. So 1 day is too big, as you'll see. If I put in 0.5, the curves move. If I put in 0.1, they move again. If I put in 0.05, they moved a little bit. If I put in 0.01, Is that going to be enough? Oh, no, that's too small because we actually ran out of steps. So let's make it 0.02. Alright, so that gets to there. I think I actually needed more steps. So let's do that. So that's actually something that does happen sometimes as you get down here and you go, oh, I actually needed more than 100 days. So let's increase this down to 10,003. Oh boy, that's a lot of steps. And I know I'm going to go too far. I always go too far. Nope, did go too far. There we go. There it goes. Okay, so now it goes out to 200 days, and I can make my time step a little smaller. Okay, so it's now showing that. If I make it 0.01, alright, so if we look at this, if I put 0.02, can you see that really the only thing that happened in this graph was that it just extended? If I make it 0.04, right, double it, let's see if it makes a change to this shape. Not really, right? The dots moved a little, but that's because of the way Excel does dots. So if I go back to 0.02, I think that's fairly good, right? So we've got a curve that's going well. All right, so that's the answer to the first part of the question. So let's save our spreadsheet. So if I click on File, Save As, and I've already got a good name, so I'll save that and replace the one I already have, so that looks good. So now what we want to do is copy the graph into Word, and the easiest way to do that is to hit Control C or Command C on a Mac, and then we can go to Word, and here's where I want to put it for question 19a. Hit Command V or Control V on my PC, and that pastes the graph in, but there's something important that you need to do before you're done, which is click here on the paste options, and if you click on the down arrow you get a bunch of choices, and we don't actually want this middle option. What we actually want is this one over here on the right, which says picture. So we want to paste as picture. And then what I usually like to do is to click on center, because I think it makes it look better on the page. Okay, so let's get back to Excel. What we now want to do is, so we should have done record your graph, so that's what we did. We just did part A. Then the next part is record the graph for RI and RR, and then there's a bunch of questions where you have to talk about stuff, so I'm going to leave that as an exercise for you. Then there's one of these yellow boxes which talks about the SIR model and the idea that everyone recovers. And then here's the graph that we just made, and then there's a graph of what you'd expect, and one of the interesting things is actually happening here. We'll be talking about that next. So question 20 is about seeing how the effect of social distancing is accounted for within the SIR model. And so what we're going to do is we're going to decrease the infection rate constant from 0.36 to 0.18, so make it half as big. Alright, and then you have to record your graph for RI as a function of time. Okay, so go back to our spreadsheet from question 19. What we want to do now is save it for question 20. So let's do that, and it's question 20. Do save. And now what we want to do, before I do that, I know there's going to be a change in the timescale, so just to make it easy for you to see what's happening, I'm going to double click on the x-axis, which is time, hit reset, which makes it auto scale. Do the same thing down here, hit reset, and that auto scales both of the time axes down here. And now what I'm going to do is decrease the infection rate constant to 1/2 of the original value and see what happens. So the first thing you should notice is that the graphs all move to the right. The other thing that maybe isn't quite as obvious is that this grey curve, if I just let it hover, there we go, the number recovered at the end is 930. which is less than 1,000, which is good because it means just a little under 70 folks didn't get infected at all. Alright, so that's that curve, and this may not quite go far enough, so I'd maybe increase this. Let's try 0.025. I'll do that, hit enter, and now we have kind of an extended period here that's definitely flat in all of the graphs, which is what we want. Alright, so file, save, and now what we want to do, let's go back to our question. Part B says let's do that, decrease this thing by a factor of a half again, and make it half as big again. And so that's what we're going to do in part B. So I'm going to do file, save as for part B. So change the A to B. And it's actually important to be saving all of these. Let me just go back. That's actually the hint here. You know, you should save separate copies, and that's one of the reasons I've been making sure I do that. Alright, so we want to change KI to 0.09. So let's do that and see what happens. So there it goes, 0.09. So have a look over here at the graphs when we hit enter. Whoa, and you'll notice that it moved a long way out. So one of the hints talks about extending the delta t because we've got a more slowly changing graph, so we can do that. So let's try 0.05. That's twice as big. That doesn't look big enough, so let's try let's try 0.1. That's actually, that would be fine. It's probably just a little big, so I'm going to just tweak it a little and put 0.075. Let's see how that goes. Alright, so that looks pretty good. Alright, so let's do file, save for part B, and then part C says do the same thing again, but now we're going to have our infection rate constant being 0.0625, which is the same as KR. Alright, so let's do that. And that was for question C, so let's do that. Oh, yes, get rid of that. Question C, so let's save this file, save as, we want it for part C. Alright, so save that. And then we want to change this KI to 0.0625, which is the same as KR. And again, when you hit enter, I like to look over here and watch what happens to the graph. And whoa, see it? It's like it's changing really slowly. So let's try making this 0.2 of a day. Let's see what that does. It's still not quite far enough, right? Because we've got this graph and it's decreasing. So let's make it even bigger. Let's try 0.5 of a day. Alright, so that's probably long enough, maybe a little bit too long, but I'm good with that. So what this shows is that the infection rate steadily decreases and eventually it goes down to 0. And the number infected is really, really small the whole time, right? So the outbreak basically doesn't get started. Just a few people get infected. Well, a few out of 1,000. But there's one rather alarming thing about this, and we'll talk more about this later. The time scale of the whole problem has like ballooned out to, you know, this is 4,000 days. Well, okay, 3,000 days, you know, in here, that's 10 years. That's a heck of a long time. So just keep that in the back of your mind because we'll come back to that later. Alright. Alright, so we haven't quite finished, so let's do file, save for that guy. That was C, and there's one more part, so let me, while I remember, do file, save as, and we're going to save it for D. And what D does is the question says, for part D, it says change KI to 0.045 days. So that's 1/8 of the original model. So if in your social distancing you're seeing only 1 in 8 people that you might have normally seen in a week or a month, then hopefully we could decrease the infection rate constant down to 1/8 of what it was beforehand. Alright, so let's see how that looks. So what was it? 0.045. And again, have a look out here at the graphs, see what they do. I'm going to hit enter. And, oh, okay, so we got a much shorter time scale. So let's make our delta t smaller. 0.0, let's try 0.05. Actually, I guessed right. Okay, so this looks like, right, there's a decent flat portion here at the end, so it's showing what's happening. Alright, so this one, and it doesn't take quite as long, it's still taking a long time, right? 365 days is a year, so that's about there. So it takes almost a year to completely get rid of the disease, on average. Alright, so that is part, let me save that while I remember, file, save. Alright, so now I've got a copy of all of those guys. Let's get that out of the way. And then I've got some more discussion questions here that you should go through and make sure that you follow. This about what you discovered, what I have is an example of how social distancing works, and I picked an example that we did not talk about just now. I picked this value of Ki, and it shows that the number recovered only gets up to just under half of the population. So it's kind of a nice pretty looking graph. Alright, then the next section is about changing the starting point, and that's worth going through. It actually explains how the initial phase of the infection, there's kind of a growth period, and you can kind of skip over that growth period but still analyze what's happening without changing very much. And then this is another really important thing, but we'll come back to that when we do the next section, what the population size does to the model. So that's another thing. I think that's fairly straightforward once you've got things working. Then I have a math question for folks who like doing proofs, and you can prove something about the model. And then this next part is really important, so I wanted to focus on this, finding the peak in the curve. So one of the things that we talked about is if you carefully look at the graphs of RI and RR, the infection rate and the recovery rate, all of the graphs where there was actually a peak, so let me go here, where there was a peak here in this orange curve. Now this orange curve and this orange curve are the same shape. They're not the same thing though, because this guy is the number infectious and this guy is the recovery rate, and they're directly related to each other even though they're different things. But the thing that happens is this blue curve always crosses through the peak in the orange curve. And so that's what we want to talk about now, because it turns out understanding what's happening at this point can give you really surprisingly deep insights into how this SIR model works. Alright, so question 25. It says, look carefully at box I in figure 1211. Well, 1211 is way back at the beginning of the section, so here we go. It's up here. There it goes. And so it says that there are two arrows, one going into box I, right, this guy, and one going out. So what I'm going to do to answer the question, let's go back to the question, 25, where is it? Yeah, coming up next, there we go. And it says we've got those two rates that we just talked about, and that you have to say, if the number infectious, so the number in box I, is increasing, what's the relationship between RI and RR? And the answer should be one of these, either less than, equal to, or greater than. Go back to my drawing program, and I'm going to draw the boxes. So here we go, we've got box S, it's got one arrow, and I'm going to label this with RI for the infection rate. The people who get infected end up, conceptually, in box I, because they're infectious, and then once they're there, they can recover, and once they're recovered, they end up, conceptually, in box R, which is the box for recovered folks. Alright, so the question is asking us to figure out what the mathematical relationship, the first one is when it's increasing. So let's talk about that. So for part A, I can go when Ni is going up, right? So Ni going up, the thing that we know, we have to have more coming in than are leaving, right? So you can think about a parking building or something like that. If you've got more coming in than leaving, the number inside is going to get bigger. So that's Ri is greater than Rr. Part B asks what would be true if Ni is decreasing. Well, in that case, we're saying that the number leaving has to be larger than the number coming in, right? So think about a parking structure again. If more cars are leaving than are coming in, then the number inside the structure is going to go down. So we're going to have Ri is less than Rr. And then the last case is kind of the transition between those two, and that's when Ni is staying constant, and in that case the number coming in has to equal the number coming out. So that just means mathematically we can write that as Ri equals Rr. Okay, let's go back and check and see if we finished the question. Alright, what's the mathematical relationship? And then part B, D, is pretty straightforward. Alright, so then the next question starts with this preamble. It says, okay, we just figured out that at the peak, the peak is the place where the number infectious, let me go back to the figure and just talk about that just for a bit. It's this figure, right? So here's the graph of the number infectious, right? This is the number infectious. At this peak, we know, because this orange curve is the same as this orange curve, the place at the peak is the place where the blue line crosses the orange line down here, and that's when the two rates are the same. Okay, so back to 26. It's always good to have a picture in your head when you're doing this stuff, so it makes sense. Okay, so that's what we've just talking about, that the Ri equals Rr at the peak, and it says by substituting these equations into that equation, show that the value of the susceptible fraction at the peak in Ni is given by this equation here. So at the moment, what you shouldn't do, you shouldn't freak out and go, I have no idea how to do that. What you should do is just follow the instructions and see what the algebra leads you to. So go down here, and we've got question 26, and we're going to start with Ri equals Rr, and then it said substitute in the equations. So you should always look them up. I did that, and here they are. We have, and so I should label that, shouldn't I? That was equation 12, and I've forgotten now, so I have to look it up. 26, right? This guy. 1226. And the other two equations, so let's just write them here. And we have the other two equations are the Ri equals Ki Ni times lowercase s, and that was equation 12.8, not 8. And Rr equals Kr times Ni, and that was equation 12.16. So the idea that the question says, let's go back to the question, it just says substitute these guys, that one and that one, into this one, which is there. Alright, so that's what we're going to do next. We're going to substitute those in. And so this guy, let's do it in a different color, green. Alright, so we're going to plug that into there, and we're going to plug that into there. And so when we do that, you get Ki NIS, right? We just replaced we replaced Ri with the other side of this equation, that guy. And then the other thing where we're going to replace Rr with that expression. So it's KRNI. Now, If you're good at algebra, you might already be able to see what we're going to do next. But just in case algebra isn't your favorite thing, let's just look at this. We've got an ni on both sides. And if we divide both sides by ni, then it goes away. So let me do that. We've got this ni and that ni cancel, and that ni and that ni cancel. And what you get left with is that KIS equals KR, and then you can divide both sides by KI. Maybe I'll write that too. Right, divide both sides by KI, and KI, man, you got to be careful when you're doing algebra. And then this guy and this guy will cancel, but nothing cancels on that side. So then what we can write is that S equals KR over KI. And the thing about this equation is it's only true if this equation is true, right? So what we want to do for this equation, let's just do this. We're going to put a P here to remind us that this is the S that goes with the idea that the two rates are constant and that we're at the peak. And so this equation turns out to be surprisingly insightful, right? It actually provides quite a deep meaning into how the SIR model works. And we're going to talk about that next. Okay, so before we go any further, I just want to say there's a spoiler alert, because what we're going to talk about now is stuff that comes up later in the chapter, but I thought in the video it would be nice to actually talk about what R naught is now, rather than wait until we've talked about other things. So, if you want to go through the chapter, you should stop now, go through the sections that lead up to R naught, and then come back. Alright, so here's my diagram for how R naught works. It's a little different from the ones that I found on the web, and part of the reason is that I actually made it quantitative, right? So we have a graph, and it has a vertical axis, which is the total number infected, and those are numbers, so we start out with 1, and as time goes by, more and more people get infected, right? So this vertical line here is when the second person gets infected, and there they are. So that's the quantitative thing that I added, because it helped me understand how this works. And so this blue initial person, patient 0, because the R naught is 2, can infect 2 people, right? So there are the 2 people being infected, and that can happen during the time period that they're infectious, which on average is 1 on this scale, because the time is time divided by the mean infectious time, right? So that gives us a dimensionless time. Alright, so this is 2 infectious times and then another about 0.4. Alright, so during that time, the first person infects 2 people, and that's the second person who's infected can infect a third generation person even before the first person recovers. And that's actually an important part of the Poisson process that is actually implied by the model. Alright, so if you just look at this, we've got each person is infecting 2 other people. I have a few orphan folks that are not included in the diagram, which makes it not quite correct, because you'd need to expand it and include all of those, but they didn't fit. So, but the number, like I said, this number, total number infected, this curve actually matches that. So here at the end of 2.4 times the mean infectious time, this last person gets infected. Alright, so this basic recovery number, it says a person infects 2 people. So how can we relate that to our model? And this is really the bit where I was talking about for the spoiler alert, because it's actually way simpler than I thought it was going to be. Alright, so R naught. R naught is this basic reproduction number. It has units of just a number. It's actually a ratio of 2 things, and we'll talk about that. It's the average number of infections caused by a single infectious person at the beginning of an outbreak. Ki, which we've talked about a lot, is the infection rate constant, which has units of per day. And it tells you the average rate that an infectious person, which we are thinking about for our naught, infects others at the beginning of the outbreak, right? When the population is basically completely susceptible. And then the last concept that we want to talk about is tau I, which is the mean infectious time. And that's the average time that an infectious person is infectious. So with those three things, we can actually figure out what R naught is in our model. So I'm just repeating the same things, right? This is our R naught, which has units of 1, Ki, which has units of per day, tau I, which has units of days. And so you should be able to figure out what to do next. We're looking for the average number of people that somebody infects while they're infectious. So this is the rate that they do it, and this is how long they're infectious. So the obvious answer is that R naught is defined as, that's what this equals with a triangle on it means, is defined as just Ki times the mean infectious time. Simple as that. Who knew? And then we can remember that the mean infectious time is just 1 over the recovery rate constant. And once we've done that, we can write this equation for R naught. R naught we can just plug in, so there's the Ki. Tau I is this thing that we just figured out. And getting rid of the parentheses, you get that, which is the normal way that you'll see R naught described. And the interesting thing is, at least for us, for me it was, is that the R naught is just 1 over the susceptible fraction at the peak in the curve. And so that's what we're going to talk about next. Okay, so now that we've derived a formula for R naught, this equation, we've talked about everything that's in it, and we can turn that around and we can see that R naught, the standard definition is this thing, and 1 over SP is the thing that we're going to talk about. So the next question, 27, is actually testing equation 1227 to see whether this ratio predicts the magnitude of the peak in SP. So that's what this question is about, and so that's an exercise to do with the spreadsheet stuff. And then once you've done that, you'll discover that it actually does a pretty good job of predicting that. And then we've got this thing SP. Maybe it isn't so famous because its name is really long, the susceptible fraction at peak number infectious. But it is related to something that is quite famous. Anyway, so it's a calculated parameter, and it tells us the fraction of the model population that have not been infected at the time of the peak, which we're going to call TP. Right? So TP is the time of the peak, and it's the peak in the number infectious. So our SP actually tells us, it's a measure, it tells us how intense the outbreak is. Right? The smaller SP, the fewer susceptible people are left when you get to the peak of the curve, which means that the outbreak is affecting more people. The larger SP, that says there are more susceptible people left at the peak, and what that means is that less people were infected. So SP gives us a really good measure, right? It tells us how well the curve has been flattened, which was one of the things that motivated this whole chapter. It also gives us a really simple way to predict how changing either of the constants, Ki, which is the one that's probably the easiest to control by social distancing, or the recovery rate constant, which might have something to do with isolation or quarantine, flattens the curve. Alright, so the concept that this leads into, which is one that I didn't really understand when I started working on this chapter, is herd immunity. Alright, so we've got herd immunity. It's a concept that you probably have heard about in the news in the last month or two. And the idea is that somehow if enough people in the herd have had the infection or are immune, then everybody is somehow protected. And before we do that, we just need to do some bookkeeping and talk about stuff. So the fraction infectious is just lowercase I. It's just the number infectious divided by the population size. The fraction recovered is lowercase r, and it's the number recovered divided by the population size. And we can do our bookkeeping equation about the three things, and now they add up to 1 because the three fractions, the three possible boxes that you can be in, if you add them up, they have to add up to 1, and that includes at the peak, right? So that's why these three things have p subscripts. So then the next thing that we're going to talk about is this h, and it kind of doesn't quite make sense that we're using h right now, but it has to do with herd immunity, so you can kind of think as h as being related to that. And what it is, it's 1 minus s, so it's the 1 minus the number susceptible. Now, anybody who's not susceptible is either infectious or recovered, and neither of these two groups can be infected, so you can think of them as being immune. So h is really just the fraction immune. Alright, and what we can do is once we get this h, the immune fraction, once that fraction reaches the value at the peak, which is just 1 minus sp, which we now know how to calculate, then the recovery rate is larger than the infection rate. And that value of h, the number immune, is called the herd immunity threshold. And it's the fraction immune, right, the fraction of the population that's immune, and if it's greater than that, then the infection, the disease is going to die out. Now, it might take a while, but it's on its way down. And I have a couple of notes. Epidemiologists would say the disease is being eliminated when this equation is true, right? So if the fraction immune is greater than that critical threshold, the herd immunity threshold, then we're on our way down. And they're using this word eliminated in the same way that we used drug elimination in chapters 2 and 4. And then who knows what people are going to figure out. Right now, April 2020, it's uncertain whether recovering from COVID-19 gives people permanent immunity. It would be really nice if that was true because, well, first of all, just from a modeling point of view, it'd be nice because it matches the model that we've got, but obviously it would also be good for people who've gone through the disease, which is pretty horrible, and be nice if they got something out of it, right, which would be immunity from ever getting it again. All right, so the next thing I want to talk about, so this is just testing the predictions of equation 1234. So that's another Excel spreadsheet exercise, and I'm going to leave that up to you. I'm hoping that's fairly straightforward. You will have to rearrange the algorithm so that it uses R naught. And there's a pre-formatted spreadsheet online that you can click on, and you can go through the activity. And then on page 31, right, so this is talking about herd immunity, and it turns out it does work the way that we think, at least the modeling thinks, but you might be a little disappointed when you look at some of the data that people still get infected even if the herd immunity threshold has been passed. All right, so the next thing we're going to talk about is this quantity S, and the little symbol here is the infinity symbol, right? So we've got S infinity, that's the way you say it, is the value, the steady state value of the susceptible fraction S in the SIR model at long times, which means that time is tending to infinity. All right, and question 32 is asking you to make a table from the data, right, from the spreadsheets that you've already made, the ones that I asked you to save, and it's got a lot of stuff in it because we can actually learn a lot of things. So record the infection rate constant, the recovery rate constant, the fraction susceptible at the peak, the herd immunity threshold, which is related to this through that simple equation, R naught, which is related to SP just by being its inverse, the number susceptible at the end of the outbreak, right? So once the curves all flatten out, how many people who are susceptible to the disease are not infected, right? So that was actually one of the motivating things for the chapter. S infinity we can get from this guy by using, where is it? Using equation 12.9. And then 1 minus S infinity, because we're going to need it in this equation, and this quantity, which at the moment is kind of mysterious, but we'll explain it soon. And I'm just calling it Y because I didn't have a good name for it, so why not? I know, it's a really bad note. Why not? So Y is just all of that stuff, and it looks very mysterious, but maybe if you've got calculus you can figure out why. We'll talk about that. Alright, so the idea is that you go through your other spreadsheets and you make a new spreadsheet and you record by hand the numbers and figure that all out. So I hope this is fairly straightforward. I'm not actually going to go through and do it. The idea is that you'll record it in your Word answer, paste it as a picture into Word. Alright. And we've already talked about, so the spoiler alert was that we actually talked about this section kind of out of order compared to the chapter, and here's the diagram. And then let's see, so here's our definition, the one that I think makes the most sense using our terminology, right? R naught is just the infection rate constant times the mean time infectious. Alright. Oh, and we have a public service announcement, so I think this is kind of fun. You should go through that. It's really a fairly straightforward little exercise. And then, so this is the herd immunity thing, and I talk about stuff and refer back to chapter 2 where we learned how to draw cool things in Excel graphs if you want. And then the explanation of how S infinity works is going through this, and I kind of would like to just go through the algebra. So it says by substituting equations 12 and 16 into 1218, show that the SIR model predicts this. Alright, so we have, actually that one's really simple. So let's skip through A and B and we'll get to the last one because it's kind of a slightly unusual version of algebra. So part C, what we're going to do is we're going to divide one equation, the one up here that we got, and equation 1245, which is this guy. We're going to divide one equation by the other. So what does that mean? Well, what that means, let's do this. We've got question 1236, 1236, and we're doing part C. And so those two equations, what you do if you just write it, I'll just literally write what it said, have one equation and do KIS minus KR delta T, and just divide by the other equation, delta S equals minus KI times S times delta T. Don't confuse the subscript with the variable. Alright. And we don't literally mean do that. We mean divide one side of the equation by the other, right? So if I do that, I get delta I divided by delta S, delta S equals, and we can write KIS minus KR times I times delta T. Did I forget the I up there? I did. That's not a good thing. You always got to check stuff while you're going through. So we want to do this in blue. This equation should have had an I outside the parentheses. So there we go. So that's that guy. And then down here we're doing that in black. back to black. Amy Winehouse would approve. Minus KIIS delta T. Alright, so that thing we can cancel the delta T's, right? No matter what they are, they cancel. And when we do that, oh, and we have an I, and the I's can cancel. And so we can write KIS minus KR, all of that over minus KIS. Now you'll notice that we have the same thing over the same thing. Now I guess I should mention, sometimes my students go, well, that just cancels out the one on the bottom and you've got rid of it. But that's not quite how the algebra works. So let's do this properly. We'll write it out. So we'll split the fraction. So we got KIS over minus KIS. And then we've got minus KR over minus KIS, which looks really ugly. Right, because that's actually a plus, the way I've written it. Okay, so this thing, everything cancels. You don't get 0, you actually end up with minus 1. And here we have minus KR over minus KI times S. So that's actually plus KR over KIS. So we can rewrite that. Let's do this back in our black color. And it's KR over KIS minus 1. And that, just reminding you what we were talking about, that's this thing. So we can then, let's just write it, delta I over delta S. And then we can move the delta S to the other side, so we can write delta I equals KR over KIS minus 1 times delta S. And did I get that right? I think I did. So 12.46. So we just derived that equation. Alright, so that was kind of satisfying. So let's go back. And then part D, which is a calculus question. So I know some of you don't have, a lot of you, most of my students don't have calculus. So this will be a little bit mysterious to those who haven't done calculus. But, and it's not actually a very easy question, you can show that the analytical solution to this difference equation, if you take the limit that delta S goes to 0, you can derive this equation. And you know, there's kind of a hint, it has a log, this log in it, and what that means is that there's probably an exponential function in the way you do the calculus. Anyway, alright, and the assumptions are that S is approximately 1 at the beginning of the model, right? It can't be exactly 1 because there'd be no infectious people to start off the infection. So that's why there's a squiggly equals the approximately equal. And we have the S equals S infinity as time goes to large values and we reach steady state. And we also have that the number infectious is approximately 0. And again, it can't be exactly 0 because then you wouldn't have an outbreak. But it's very small at the beginning, right? So 1 person in a million, that's pretty small. Or even 1 person in 1,000 is actually pretty small. Alright, so that's at the beginning of the model, and at the end of the model, the number infectious dies out, right? Because if there are any infectious people, there'll be more infections. So we have to wait until this number ends up being 0 to reach steady state. And just reminding you, we've got R naught, which is defined by equation 1242, right? Equation 42, if you like the Hitchhiker's Guide to the Galaxy, it's the answer to life, the universe, and everything. Who knew? Okay, so then once you do that, we've figured out something actually quite important. So that's what this box is about. It's just talking about this basic reproduction number, naught. And this is another reason why it's such a useful concept, apart from being something that's kind of intuitive. It lets you figure out, using this equation, if you know R naught, you can find S infinity, but it's in this equation in two places, and as I mentioned here, there's no way to use algebra to solve for S infinity. So it's one of those things that in regular algebra classes, they kind of just make you think algebra can do anything, but there are some problems you can't solve using regular algebra. And it turns out that Newton, way back when, figured out a numerical way of getting the answer for S infinity. But we've already done that. Right? We did it in our spreadsheet. We actually had a little numerical method that solved the model, and we found our values of y. Now, I redid this, the problems, and because I was trying to see how well it would do, instead of using like 15,000 rows, I did 32,000 rows, which is like kind of crazy big. But what it did was it made these values of y, you'll notice they're all really quite small. And the last three here are actually, they're consistent with what the value of S was at the beginning of the problem. Remember, the approximation is that, the value of I, the approximation is that at the beginning of the model, the fraction infectious is 0. But in fact, if we had 1,000 people and we started with one infectious person, that's off by 0.001, which is actually the same magnitude that we have here. So the fact that all of these are in that same ballpark tells us that it looks like we've figured out how this S infinity is related to R naught with our equation. And we also have over here some other quantities that are worth talking about. R naught can be any value, right? It can be bigger than 1 or smaller than 1. But the herd immunity critical threshold has to be a fraction. And so once you get to R naught of 1, the herd immunity threshold is 0. Basically, you've got herd immunity from the get-go if R naught is 1. And if R naught gets even smaller, the math predicts a number that's negative, but that doesn't make any sense, so it's just 0. Same thing for the fraction at the peak. The peak occurs at the very beginning, and it always decreases. So that's why both of these are 1. Alright. So that's pretty much where I got to at the end of section 3. The next thing we're going to do is to actually talk about trying to match up our quantitative model that we have and compare it to real data. And it turns out there's a thing in meteorology called the butterfly effect, and it actually relates to when I first started trying to fit this model in early April. I was kind of surprised by how sensitive it was to the data. Like the fit would change from day to day. So we're going to talk about that next. And then in section 5, we'll actually talk about making a prediction for what's happening in May of 2020 based on the first 3 weeks of April. All right. So I think that's where I want to stop. Yep. So if you survive this really long video, take a rest. I will be publishing section 12.4 as soon as I get it finished, and I'll come back with a video once that's done. Okay, so don't forget that all the resources for this project are at circle4.com/biophysics, and at the top of the page you can find links to the chapters and the videos.